Hey guys, here is an important result from last lecture. We went through some math and obtained this concept. Actually, they are theorems now. If we have a PAA parameter adaptation algorithms using the series parallel structure, for example, recursive least squares, then if the adaptation gain is slowly vanishing and UK is rich in frequency, it's persistently exciting, and independent from the noise, WK plus 1, then, and WK plus 1 is white noise, then we will have unbiased convergence of the parameter estimation. That's unfortunately not always the news. Usually, we can't expect the white noise in the series parallel structure from the block diagram that we drew. So, in practice, usually, if we focus on having a really good parameter convergence, we want theta hat to converge to theta, then this parallel structure is usually the preferred method because it's going to have easier conditions to have unbiased convergence. UK needs to be persistently exciting, and it doesn't have to be independent from this condition is removed, and the whiteness condition is also removed. The only thing that's needed is UK to be independent from WK plus 1 statistically. So this is better convergence. However, as you can imagine, there are more stronger conditions for stability analysis. For this one, recursive least squares always guaranteed to have convergence, but this one has stronger SPR condition to satisfy. All right? So you have to, in practice, usually you always have to sacrifice between performance and stability. All right? So usually you have to meet stability first to start with. That's the two results. And another thing that's relevant from past lectures is this concept where we said a practical mechanical system usually will have, the plant will have a one-step delay inside, and equivalently you will be having this result where your control input actually doesn't impact your current output. Think about it this way, because some of you had questions. Think about it this way. Your control input, UK, does not directly impact, so think about it this way actually. Your control input U plus 1, UK plus 1, doesn't directly impact your YK plus 1 output, all right? Because of this delay, we said in practice a way to generate this delay is the zero order hold signal. But delays can happen in many ways. Think about the physical intuition. If there is, today we have rain, but in the morning maybe the rain wasn't even here, but we see there's a cloud, let's say 3 miles away. The cloud is physically there, right? But the cloud at 8 a.m. is not giving us rain. It may give us rain 3 hours later or something, after the cloud has moved to Seattle area, right? So delay happens in this fashion. Delay can also happen in a communication way, right? In the old days, when you call someone across the country, there's a few seconds delay for the other person to hear from you, right? So your measurement can also have delays, right? So that's how physically this scenario can happen in practice, right? So that's for this small thing from the past. Now, today, two things to talk about. First is we see this kind of trade-off between stability and performance. Now, obviously, someone will try to bridge the gap between these two. Someone will say, can I have good stability criteria? And in the meantime, I can have some better convergence condition, right? So there are some of these methods. I'm going to talk about one of them. All right, it's not the only one, but it's something that's quick and easy to to derive. So one way to bridge the gap is this method called extended least squares. Least squares is nice, but it doesn't have good convergence out of the box if you have noise inside. So someone said, can I extend it so that I can have good stability as well as some reasonable convergence under certain practical conditions? So the assumptions are we have input and noise. The noise has this type of structure, is a white noise filtered by some filter, C over A n k plus 1. And then this is y k plus 1. So suppose we have this type of system structure. This is white. Then it goes through some kind of filter over here. Equivalently, this is saying that yk plus 1 is, I'm going to write it out. It's essentially a series parallel type of structure. If you treat it this way, write this out. And then notice the common denominator in these transfer operators. So these are essentially very much similar to standard recursive least squares with an added term. And the overall idea is I'm going to try to identify all these parameters in A, B, and C. Then, because this is white, so that's a good news to us. All right? So we have y to be equal to, let's write it in the regressive form. The first two parts are essentially the same as before, right? So let's say A is 1 plus A1, etc. And B is B0, B1 to Bm. And C to be nth order, so C1, Cn sub C. Okay, so these are the orders. The order of C doesn't have to be the same as order of A, which is different from the previous PAA with an adjustable compensator. Now, let's write out yk plus 1, how it equals to the rest. The first two parts will give us exactly the same thing, so you can expect negative A1 all the way to AN. Then the right-hand side is standard. Then the last term is going to be the noise term. It's going to be C operating on this white noise. So it's nk plus 1, C1, nk, C2, CNC, nk minus nc plus 1. All right? Just some simple filtering operation using the transfer operator. The first two components, these are exactly the same as before, so they can be written in a way of phi k transpose theta. Let's modify the regressive structure a little bit to write it in a more compact form. We're going to define it this way. I'm going to write it this way. Phi k, essentially I try to combine all these in a one regressor, one data vector. So I'm going to write it as this. Phi k, nk minus 1. This new regressor vector containing this data times theta, and then adding these unknown parameters C1, C2, C, and C. Okay? Here is only counting the parameter, unknown parameter C1 to C and C. There's one element that I intentionally left out, which is nk plus 1. This is feasible to write it, but slightly different in terms of now the implications. I know yk plus 1, all the previous noise will make an impact into yk plus 1. So if I measure this signal, I will gain some impact of these terms will show up in here. And in turn, there will be a way to somehow estimate these parameters from this measurement. All right, so I can design, in other words, I can design my estimation to be like this. I can make all these to be inside, use the same type of regressor vector, and then do theta hat. All right? There's not much of a way that I can get a good estimate of a white noise. So the best way to do is reasonably just to do this. So that's the first intuition, to do this extended least squares by including these additional noise dynamics. Now, there's some bit of trouble still. Can anyone see? Naively, this would be a good prediction, but someone write a code. How would you do this? It's something that's not so easy to obtain in here. Someone look at this and thought about it this way. So they are not directly measurable. However, if this, let's call this extended vector to be theta e, if, however, these two are pretty close to each other, then we can have this result. We will have, except the noise term, the other terms will be relatively close to each other. then we can have epsilon, this estimation error, a posteriori estimation error, to be approximately equal to the noise term. Again, the intuition is if these are reasonably close to each other, then the first part will be relatively close to each other. The remaining term is the difference that can be approximated by something that we compute, the a posteriori estimation error, epsilon, adaptation error, epsilon k plus 1. The approach, so this is an approximation. And statistically speaking, a lot of approximation actually will happen in practice. But the good news is if you adopt this approximation, then we can do, instead, we can do phi, we can essentially have some way to observe or estimate these unmeasurable noise terms. So we do instead use the a posteriori error to construct the regressor vector. And then theta is the same theta. And then do recursive least squares based on these. Y hat, the a posteriori estimation to be phi theta hat. All right. And then the usual way of recursive least square update. And then the same equation for the adaptation gain. So that's the extended least squares. Now, the important things are this has guaranteed stability. So the SPR condition is actually automatically satisfied for this type of structure. This is one way to try to have a balance between these two. Another way to get a balance is the method that we already actually discussed, is the parallel. This is still a series parallel structure because the regressor vector phi is using these actual measurements. Another way to bridge the gap is actually the parallel method with an adjustable compensator. All right, over there, this phi vector is actually using the estimated output. But the trick that's played over here is you are using the more statistically friendly estimated output in the phi, but you also add these adjustable compensator portion. This is also extended. All right, so by doing some augmentation of the model over there, we actually get, this also has guaranteed stability. And reasonable convergence under these assumptions. If your system can actually be modeled this way, then this will have good convergence. And if in practice this is not the true system model, the convergence will, usually we call local convergence. You cannot have global estimation correctly. But if these are reasonably close to the true parameters, then you can have good convergence. In practice, one way that people would do to counteract the local convergence is to first try to get a good, reasonable, not 100% accurate, but maybe 50, 60, 70% accurate version of the parameters by, let's say, standard least squares. All right, they run a less accurate algorithm first to get an initial good condition for the theta hat vector. Then they initialize with this something that's better than 0. So these are just two examples, but depending on how you model the system, there are other ways to get a better convergence. And these are usually done on a case-by-case condition. These are the general principles behind trying to get a good convergence under stability conditions. There's another class of practice that is really very helpful. The other class of practice is, let's not focus too much. Let's think about some other scenarios for disturbances. In practice, there are cases where disturbances are not purely wide. They can have other structures. For example, IMU sensors, they may drift, right? And have a little bit of idea of how the signal will drift. Those are not white noise, but they are actual noises. So let's see how we can do good parameter estimation giving some knowledge of the noise signal. So this falls into the category of system identification with deterministic disturbance structures. Let's use this example where we have a constant disturbance going into the system model. Suppose this is a constant, but we don't know what the exact value this is. So that's actually turns out it will be very easy to handle this kind of scenarios. First, let's write out the system output. We have A yk plus 1 is A operating on D plus BU. Oh, there's a typo. It should be 1 over A. All right. So is similar to recursive least squares with just the one extra disturbance D. And we can write it in the regressive form, again, as so essentially repeating the write-up on the right-hand side of the board. And then this d term. All right, so it's essentially the same thing, exactly the same thing, phi k transpose times theta plus this extra noise term. There are two ways to do this. The first way is to do something similar to this. I'll try to enlarge or augment the regressive structure to include this unknown. All right, so approach 1 is I'm going to define phi e to be phi and then 1, and then theta e to be theta and d. All right? So starting from this lecture, you will see more and more things like this, where you augment the regressive vector in a way that these are not necessarily what you measure exactly. Okay? You can see, you can construct this regressive to put y in here, and then add d to theta e. This will give you yk plus 1 to be the same as phi e transpose k theta e. And then this is perfectly the same structure that we see in standard recursive least squares. So we can run any kind of PAA for the estimation. So that's the first approach. The advantage is you're going to be able to get a good estimate of d in the end. The disadvantage, if you insist to find some, is the matrices, the dimensions will increase. Theta e has increased 1 dimension, the same as the adaptation gain f will increase its dimension 2. So the computation is slightly more involved. Another way to do the parameter estimation is so-called filtering method. And that is a very common way and useful way to do. We talked about, in one of the lectures, we talked about this concept of low-pass filtering. A constant doesn't have any high-frequency components. It is always a constant. It doesn't change its value. And this is actually a form of low-pass filtering. It will filter the DC gain component of its input signal. So carrying out the operation, you will see one operator on D is D. One step delay of a constant is the same thing, so it's 0. Okay? So if you see that, then you can construct a filtered output, let's say YF. And then UF filter both the input and output by the same filter. The relationship between these doesn't change. Then we will have YF k plus 1 equal to, I'm going to bring this equation to the computation here. So it's going to be equal to phi theta plus d, and it equals a term without the constant disturbance because of the low-pass filtering happening in here. All right? And then let's write it in a slightly more detailed way. It also equals, we have the phi vector. Let's write out the phi vector in here. Negative yk minus n, uk minus m. This is the true parameter, and your filtering actually goes inside here to these signals. So it's going to be equal to this go inside to operate on yk, and then operate on uk in the end. What is this filter operating on yk? Is negative yfk, right? And then go down this list. It's going to be negative yf k minus n ufk all right? So this is, if you do this kind of filtering, you have everything actually filtered. So you can run this, right? Now this is a really standard series parallel type of model, right? Y, UF, everything is filtered. So you can run PAA on new model, on new regressor. So this is, if you have a constant disturbance, you can quickly remove the influence of D by this filtering. And the dimension is kept. You have the same dimension theta. You don't have to enlarge the dimension of the computation. This is for one type of disturbance. Now, in your exercise or your extended reading, you will see scenarios. This also works. Let's write it this way. This can also work for the scenario where dk is, let's say, sine or cosine. All right, so if you have something like this, this is actually also can be easily filtered out by something like this. I'll give you some hint with filtering of right, so you can remove the influence of these kind of disturbances by pre-filtering the signals by here, this structure. And you have actually seen this before. Remember in the persistent excitation analysis, you have actually seen this type of filtering happening. All right? Rationale there is that if your input is a sinusoidal signal, then this type of filtering will completely remove this single frequency component. Okay, so that's about it for today.